Hello, everyone. So I'm going to talk about some joint work with Stefano Gogioso. It's on the Sheaf-Theoretic structure of definite causality. So before I start, I have to review some fundamental things about the Abramsky and Brandenburger framework for contextuality and non-locality. So we start with a set of measurement X, which denotes all the possible measurements that some set of agents can do in an operational scenario. And then we define a measurement cover, which is a family of contexts, which covers this set of measurement. So it's a family of subset of X, which define the compatible measurements. So the measurements that can be performed somehow together. And the union of those sets of measurement has to give back X, of course. So every element of X is in one of those sets. And then we fix a set of outcomes, which can be fixed, O, let's say. So the next step is to associate to an arbitrary subset of X all the possible functions from the measurements to the outcomes, deterministic functions, okay? So those are deterministic assignments of outcomes. We can assign the set of all deterministic assignments for every subset of X, and it actually forms a contravariant functor for the people who are who know about category theory. And in particular, this functor is a sheaf, meaning if you have like different assignments if you choose an assignment, a deterministic assignment of outcome for different contexts which agree on their intersection, okay, then it is possible to consider a global assignment of outcome for the scenario given by the union of all those contexts. And it is possible to define this global scenario uniquely. This is always possible with functions, okay? It's always allowed to glue those functions to form a bigger function if the function agrees, if the two functions agree on the intersection. However, this is not anymore the case when we become probabilistic. So when we compose this sheaf of events by the distribution monad. So this is also a pre-sheaf, but it's not a sheaf anymore. So this uniqueness of gluability is not anymore there. So what we do here with the distribution monad, we associate to each set, not the kind of deterministic outcomes, but we associate a particular probability distribution over the deterministic outcomes. Now, this is not a sheaf in a similar way, like if you have a kind of, let's say, a classical entangled state, or a quantum entangled state, you cannot reconstruct the entire statistic from the marginals. Okay, there are different ways you can glue them together, or there might not be ways to glue them together, and this is what happens sometimes with quantum scenarios. So if we have a cover, so a measurement coverage, which tells us what are the compatible families of measurement, then one set of distribution for each element of this cover, one choice of distribution over the outcomes for each element of this cover, which agree on intersection, forms what we usually call a compatible family for the pre-sheaf. Now, this is a kind of mathematical notion, of course, but it is interesting that this mathematical notion is corresponds precisely to something which can be operationally well defined, and it is well known. So no signaling. So consider, for example, that you have two space-like separated agents, Alice and Bob. They can choose either to perform A0 or A1. So Alice can choose to perform either A0 or A1, and Bob similarly either B0 or B1. So if we now consider what are the possible contexts, so what are the measurements that can theoretically be performed together, we see that those are A0, B0, A0, B1, A1, B0, A1, B1. okay, which correspond to all the possible local choices of measurements. So the set X is composed by 4 elements, A0, A1, B0, B1, okay? Then we define this, measurement cover, which are those sets with cardinality 2, which are the measurements that can possibly perform together. Now, the no signaling in this case is equivalent to this actually observation. If we have two, sorry, this should be an intersection. Actually, there is a union. It's wrong. But if you have two contexts, and in both of them there is A1. So in both of them, Alice decides to perform A1. Okay. In one of them, the choice of Bob is B1. In the other one, the choice of Bob is B0. So the fact that those two contexts have an empty intersection, which is A1, implies that, well, if we marginalize the outcome of Bob when Bob chooses to perform B1, or if we marginalize the outcome of Bob when Bob chooses to perform B0, we obtain exactly the same conditional distribution for Alice. This is no signaling. Now, the Samson-Brandenburger approach can readily be generalized for general non-locality. So consider the case when you have n agents, they are space-like separated. So in this case, like we have denoted the diagram this way. So it is not possible to communicate directly between the agents, but they may have some shared resource or whatever. But the scenario satisfies no signaling, okay? Now this can be analyzed in this Sheaf-Theoretic perspective by taking the set of events to be simply the disjoint union of all the local inputs that can be performed at the local inputs for each agent, which is given. The disjoint union is simply like a union of all those inputs, keeping trace of where they are coming from, okay? Now the measurement cover, which is a generalization of the cover that I was describing for the bipartite case, Alice and Bob, is simply, so it's a collection of sets which are indexed by a particular choice of measurement for each agent, okay? So we choose the measurement X for A0, we choose the measurement Y for agent 1, and so forth. So one of these choices, okay, select out can be considered as a subset of those elements X, and the union of all those choices is actually equal to X itself. So it covers all the possibilities. Now we define also the sheaf of events, which is simply, you know, assigning all the possible functions from the inputs to the outputs, deterministic. It's the same as we said before, but now we have more structure. You know, now we're just saying that the set of events actually has more structure. It also has the information about the locations. Now, Abramsky and Brandenburger show that if you have an empirical model for a measurement on a measurement cover for a distribution functor, then having a global section is the same as having a realization by a factorizable hidden variable model. What is a global section? A global section is an assignment of a distribution of deterministic outcomes for the biggest element of the power set, so X itself. So you assign for every single measurement, you assign a function which associates outcomes. You assign a distribution of functors which associate deterministic outcomes for every single choice of measurement. This is exactly factorizable hidden variable model. So what Abramsky and Brandenburger show is that there is this kind of very neat correspondence between the mathematical language of sheaf theory and the idea of having a a factorizable hidden variable model. So a diagram of a classical theory which realizes the no signaling correlations. Now, we want to go slightly beyond this. We want to study situations where there is not only no signaling, but also some causality, some signaling, some definite causality going on. And for this reason, we define a causal scenario, which is a finite poset, the causal set. And for each element of this poset, so for each event, the elements of this poset are effectively event, we have a set of inputs and a set of outputs. So this can be diagrammatically described in this way, where the dashed lines represents the inputs and the outputs that we associate to every event, and the arrows indicate the causal relationships between the events. Okay, so now suppose that we want to apply the same machinery that I was describing before for non-locality, even also here, no? So to have the idea to extend all these kind of Sheaf-Theoretic formalisms also to those situations where we have non-trivial causal relations between the events. Now it may sound a bit problematic, and why? Like, suppose that we take the events to be the disjoint union of the inputs, okay, as we've done earlier. And now we take the power set of this set. Then all the set of inputs for Alice actually induce a well-defined conditional distribution. Why? Well, it is enough to marginalize the output of Bob. We have no signaling from the future. So the distribution at Alice sites will be independent of everything that is done at Bob. And this is a subset of the power set of the disjoint union, okay? Now, however, we can have signaling, we potentially can have signaling from the past. So there is another context, which is IB, all the inputs at Bob's side, which do not form anymore a well-defined distribution, conditional distribution. Why? Well, the output of Bob can crucially depend on the input of Alice. So there is no way really to form a well-defined distribution for the contexts, the measurements of Bob, okay? They don't form a well-defined conditional distribution. So what we need is a kind of a topology, so a structure of containment in the set of contexts, which takes into account the restriction imposed by no signaling, by signaling actually. So how do we do this? So consider, for example, a causal set, so just a poset omega shown in the slide A, which is allowed to communicate to Bob and Charlie. Okay, imagine we can always think about those things as events in space-time. Okay, now the lower set of this poset is the set of all the subset of the elements, subset of events, okay, which entirely include their past, okay, which are downward closed. So we have some examples here, like ABC, it's a downward closed poset, there is nothing, everything is in there. A and B, A and C as well, okay, and also A. C is not, of course, because the set C does not contain A, which is in the causal past of Charlie. So how do we define this our version of the power set of events, no? This locale of inputs? Well, an element of this locale is specified by a particular choice of lower set, this lambda u. Say that the element is u, okay? It's specified by a choice, lambda u, which is a choice of causal set. And for this causal set, for every event in this causal set, just a collection of inputs. So a set of things that can be done, okay? So this is a locale. So one also needs to define a an intersection or an union, but those are just a set-theoretic analog. It's like if you want more information, you're welcome to check our paper. And we also need to define a containment relation. So when such an element, okay, defined by the choice of causal set and choices of possible inputs for each of the elements of this causal set, okay, when is something like that contained into another one? Well, this happens if and only if the lower set of, so suppose V is less than U, V is contained in U, when the lower set of V is entirely contained in the lower set of U, and for every element of the lower set of U, the input that you have chosen are contained in the inputs chosen in the bigger context, okay? So this forms a locale, and we need here to define the analog of what are the kind of deterministic joint outcomes. So we need to define for every element of this locale an assignment of deterministic joint out, the possible deterministic outcomes. So this is given by the following. So given an element of the locale, we associate with the set of all the functions from its joint inputs, to its joint outputs, because remember, every element of U will have some specified inputs and some specified outputs, okay? But we require the function in this set, we require them to be causal. So what do we mean by causal? Well, we mean, consider the case where Alice is allowed to signal to Bob. The causal function for this causal scenario are the ones where the output at Alice's side depends only on its inputs, while the output only on Alice's inputs, while the outputs at B, Bob's side, can depend both on Alice's inputs and on Bob's inputs. This can be defined as, so this is a kind of a diagram, like we are basically describing a diagram in set of with this shape, okay, where this is copying. This can be generalized to arbitrary causal scenario, and it's a combinatorial property of the data, of the deterministic data that we assign, okay, our sheaf of section. Now, we can show the following, that when sigma is a non-locality scenario, so where the underlying causal poset is actually is the discrete one, okay, and we take X to be the disjoint union of all the inputs, then we have the locale, the power set of X, okay, and the locale described as we described it are actually isomorphic, are actually the same thing. And also the assignment, you know, the assignment of the deterministic function described a la Abramsky Brandenburger is equivalent to our assignment. So this shows what we're really doing in considering this more complex causal scenarios is a generalization of the Sheaf-Theoretic framework for non-locality and contextuality, which maintains the expressive power of the original one. Given sigma, a definite causal scenario, we can define to it a kind of canonical cover, similarly to what we have done in the case of non-locality. So what we can do is we take all the elements of the locale which contain the entire causal structure, okay, and for each node, for each causal event, there is only one choice of input. Those are elements of the locale. If you take the entire family of those elements, you get a cover. And an empirical model is a compatible family for this particular cover, given a definite causal scenario. So what we have is a table of probabilities where the rows are indexed by the inputs, by the joint inputs, and the columns are indexed by the joint outputs. And we require it to satisfy a kind of a causal extension of no signaling, which is which can be deduced by the structure of the locale, but it's actually very simple. It's just so if you have two elements which have some common lower set, okay, then it is possible to pass to the common lower set from both elements, and what we get is a well-defined distribution. Now, we observe that the observation of the original Abramsky and Brandenburger paper can be carried on in this case. Okay, so if you have a definite causal scenario and an empirical model for the causal scenario, okay, then a global section is precisely a hidden variable model. So what we are saying that if we have an empirical model which has a global section, then what we are saying is that the empirical model can be simulated by a classical diagram with the same causal structure as it is shown in the slide. We have a kind of a definite causal scenario on the left and a classical causal diagram which is compatible to the definite causal scenario. So when the model has a global section, then it can be simulated classically, okay, with a kind of possible, like with some classical conditional probabilities at each causal location, which may share some hidden variables. Now, let's consider a small example to understand what is this framework about. So suppose that we are taking the definite causal scenario shown in the slide. And we are performing a particular protocol. So we are letting Charlie select the ZZ parity of a Bell state. So if the input of Charlie is 0, then he prepares a mixture of phi plus and phi minus. If the input of Charlie is 1, he prepares a mixture of psi plus and psi minus. Then he measures the XX parity of the state. So what happens is that the quantum instrument outputs one of the 4 Bell states, and then Charlie sends 1 qubit to Alice and 1 qubit to Bob. And then Bob, with their choices, with their inputs, can choose to perform either a Z or an X measurement on the qubit. So what we obtain is a conditional probability like this, where the rows are indexed by the choices of the agents. The columns are the possible outputs. Like the probability table like this doesn't tell you much, but then if you perform some analysis, you realize that this table describes empirical models for the following 2 causal scenarios, which are contained in the causal scenarios that I was describing earlier. So this means that, and moreover, it can be shown that the empirical model is local. So there exists a global section. So what does it mean? When it means that one can find a hidden variable simulation, okay, and one could find it either in one direction or in the other, actually. And we have shown how the simulation works. So you see that the causal structure is respected. We have Charlie, we can send some bits to Alice, okay. The hidden variable are just those values for Z, X, Y. They can be gathered together into one single hidden variable. But it is interesting, that if Alice and Bob choose to perform something else, so for example, the Bell measurement, then suddenly the empirical model ceases to be local and the hidden variable simulation cannot be realized, okay? But it's about how it is possible to simulate a scenario with a specific causal structure, no? So why is this framework useful? What it is useful for? So first of all, a systematic anatomy of causality emerges. What do you mean by this? We can associate to all those posets the set of the convex polytope of the scenario which are compatible with these definite causal scenarios. And as those kind of posets are nested, can be nested one into the other. Similarly, also the polytope structure inherits this nesting. So like it is possible to, like, given one table, one of those table of joint probabilities, to analyze it with respect to all those possible causal order, to see what is the fraction which is supported by one or the other, and perform some causal discovery. Moreover, it is possible now to study the interaction between causality and contextuality. We have a framework when they are put on the same footing, really. Like, for example, you can also explore a situation that we usually define as contextual scenarios by just taking different covers. We were in particular talking about locality, but this can be extended also to what we generally mean by contextuality, but in scenarios with where the causal dependency is actually important. Now, this entire procedure is easy to generalize to indefinite causal order. So to provide a kind of theory-independent description of the phenomenon of indefinite causality, if we wish, and also a theory-independent verification of it. But this is also left for some future work. This can give some rigorous treatment of cryptographic protocols, but it can also help us understanding quantum advantage, both in the kind of standard circuit framework, or when adding this feature of indefinite causality, which which one is able to identify in a theory-independent way by basically just tweaking minimally what I have shown to you until now, and just passing from posets to preorders. And well, and also I guess like if anyone has any suggestion or clarification, or if anyone wants to talk about this framework, you're welcome to contact me or Stefano. We are really happy to talk about this. So I hope you enjoy this presentation, and thank you for watching. Thank you.